Hello. Before we get into the content of this module, I'd like to take some time now to recap some of the mathematical foundations you may have learnt in your previous studies, so in the previous prelim module or in your school studies. And these are the kind of things and techniques that are going to be useful throughout this module. So I also want to make sure that we've got those strong foundations right at the start before we get going. Some of the things we're going to be looking at are doing arithmetic with fractions, solving algebraic equations, and then being able to understand the summation notation. So these are going to be used throughout this module. So first we're going to look at fractions, and I've got a couple of questions here just to recap how we deal with fractional arithmetic, and I'm going to be doing these on the whiteboard. So if you look at the first question here, it's just asking us to simplify a fraction. What does simplifying a fraction mean? So the question asks us to simplify 70 over 84. What do you mean by simplifying a fraction? Well, you would have seen before there are lots of ways of writing the same fraction. For example, a half can be written as 3 over 6. Because 3 divided by 6 is a half. It can also be written as 7 over 14 and so on. It's much more useful to be able to write it in its simplest form, and a half, 1 over 2, is the simplest form of this fraction. What do we mean by the simplest form? Well, there are no common factors between the top and the bottom of this fraction. So we'd like to do that with 70 over 80. So let's start by writing down 70 over 80. And one of the simplest ways to simplify a fraction is to take the top and the bottom of this fraction and write it down in its prime factorisation. So we can write the top as, well, 70 is 7 times 10. And the bottom, well, that's a bit more work to work that out, but we know it's an even number, so we can divide it by 2. So that's going to be 2 times what? In this case, that's 42. We can break this down even more. So 7 times 10 is 7 times 5 times 2. And 2 times 42 is 2. Again, this is an even number. Times 2 times 21. And 21 we can split out again. Now you'll see that the top and the bottom have some factors in common. There's both a 2 and a 7 on the top. So we can cancel out the 7s and cancel out the 2s, and we are left with 5 divided by 2 times 3, which is 5 over 6. And so the fraction 70 over 84 can be written as 5 over 6. The next question asks us to multiply two fractions. And multiplication is one of the simplest things we can do with fractions. If we are multiplying fractions, we simply multiply the top and multiply the bottom. So 3 over 7 times 5 over 33 is going to be 3 times 5 over 7 times 33. And again, rather than write this out fully, we can simplify this. So how would we simplify this? Well, we can keep it in its prime factorisation form. And 33 can be written as 3 times 11. There's a 3 in the top and the bottom. You can cancel those out, and this becomes 5 over 7 times 11, 5 over 77. Next, we are asked to divide two fractions. We want to divide 5 over 12 divided by 3 over 2. Dividing fractions is the same as multiplying the first with the inverse of the second. Now recall that the inverse of a fraction, we simply switch the top and bottom. And now we can multiply as before and simplify as needed. And the last piece of arithmetic with fractions we're going to look at today is addition. In order to add two fractions, so here we have 12 over 5 add 4 over 3, we are going to want to make sure that they have the same bottom. Now how do we do that? Well, we can multiply 12 over 5 by 1. That doesn't change a thing. And we can multiply 4 over 3 by 1. And that doesn't change a thing. Why have I done that? Well, I can write 1 in lots of different ways. 1 is just 5 divided by 5, or 3 divided by 3, or 100 divided by 100. And we know when we multiply fractions, we multiply the top and bottom. So we can use this technique to make our bottoms the same. So we'd like to have the same bottom. So if we could multiply this by 3 over 3, we'd have 3 times 5 on the bottom. And this by 5 over 5, we'd have 3 times 5 on the bottom. Okay, now do the multiplication. What does that give us? That gives us 36 add 20 over 15. Simplify. And 56 over 15 is in its simplest form because there is no 5 or 3 as a factor of 56. Okay, so that was fractions. We are now going to take a recap at algebra. So algebra is the maths of unknowns, and sometimes we are just trying to simplify, sometimes we want to solve to find values for the unknown which satisfy certain conditions. So here we have 3 questions. First we're going to simplify an algebraic expression with 2 unknowns, x and y. Then we're going to solve an equality, then we're going to solve an inequality. So let's look at the first question. What is the first thing we can do? Well, we can't do the whole prime factorization thing, so everything's sort of split out as it is. But remember when we had prime factorization, if we had a 2 on the top, we could cancel it with a 2 on the bottom. If we had a 2 multiplied by 2 on the top, we'd only cancel one of the 2's out. Yep. So we can do the same with the x's and y's. So let's take each thing in turn. So we have a 3 on its own. There is no number on the bottom. Let's have a look at the x's. We have x squared divided by x. X to the power of 2 divided by x to the power of 1. Dividing powers, we take the powers away from each other. Same with the y's. Y to the minus 2 divided by y to the 1. Right? After all of that, we take the square root of x. Now what do we know about powers? X to the 2 minus 1 is just x to the 1, so that's just 3x. Y to the minus 2 minus 1 is y to the minus 3, so that is divided by y cubed. Then we add our root x. Usually when we simplify, we'd like to express this as one fraction. It's usually much easier to deal with. So now, just like we did when we were dealing with fractions of numbers, we'd like to add 2 fractions here, make it one fraction. We want the bottoms to be the same. So the bottom in this case is just 1, but can we multiply this by the top and bottom of this by by something to give it the same bottom as this, or we can multiply it by 1, which in this case can be written as y cubed over y cubed. And now we can just add the fractions as we did before. In the next question, we are asked to solve an equation, the equation being 4x plus 5 is equal to x minus 7. What does solving an equation mean? We want to find a value for the unknown in this case being x. So we want to find a value for x which satisfies this relationship. All an equation is a relationship. So which values of x satisfy this relationship? In this relationship, everything on one side of the equation is equal to the other side of the equation. So if we do something to one side of the equation, and we do the same to the other side of the equation, the relationship will still hold. As we start doing this, we can start to rearrange this equation. So if we add minus 5 to both sides, so 4x plus 5 add minus 5 is equal to x minus 7 add minus 5. Now we could add minus x to both sides. So 4x add minus x is equal to x add minus x minus 7 minus 5. How many x's do we have on this side? We have 3 of them. How many units do we have on this side? We have minus 12 of them. Can we divide both sides by 3? So if this side is equal to this side, a third of this side is going to be equal to a third of that side. So divide both sides by 3, we're going to get x is equal to minus 12 over 3. And minus 12 divided by 3 is minus 4. That's a solve that equation. Okay, and the last question in algebra asks us to solve this inequality. It's an inequality because instead of an equal sign, we have a greater than or equal to sign or a less than or equal to sign. So this inequality says that 2x plus 2 is always greater than 4x minus 8. Which values of x is that true for? So just like an equation, we can add or subtract things from both sides and it doesn't change the inequality. Now if we take minus 2 away from both sides, and if we take minus 4x away from both sides, now let's simplify both sides. How many x's do we have here? We have minus 2x of them. How many units do we have on this side? We have minus 10 of them. So now what we would do with an equality, we would divide both sides by minus 2. But dividing by minus 2 is a negative operation. It's a negative function. So when we divide by minus 2, we need to flip the inequality. Minus 10 divided by minus 2 is 5. So in this case, this equation is satisfied for any x which is less than or equal to 5. Finally, we're going to look at the summation notation. This is usually something that when you haven't seen it before can be quite difficult to get your head around. So let's just recap that here. So the summation notation is this Greek capital sigma sign, and what this is telling us is that we're going to take, you can see my cursor, we're going to take every value of I from minus 1 all the way up to 4. We're going to apply this function to xi and we're going to sum them up. Now what is xi? So the x's are usually part of some sort of series. So it could be, for example, the natural numbers, and xi would be the ith natural number. So example here, we apply this function to every x in that series from I equals 1 to 4, so x1, x2, x3, x4. We apply the function f to that and then sum them all up, add them all up. We don't usually write it like this. We don't usually write the sum of a function f. We usually write out that function explicitly. So for example, the function could be x squared over I. So here, the sum of xi squared over I, and imagine these are the natural numbers, we'd go, was the first natural number squared divided by 1 plus the second natural number squared divided by 2 plus the third natural number squared divided by 3 plus the fourth natural number squared divided by 4. We don't always have to start with I equals 1. We can go from any number to any number as long as they're increasing. So for example here, we can go from I equals 1 all the way up to 7. Sometimes we don't have to have an upper limit either. We can go on forever. So we can go from I equals 3 to infinity. Now when does this make sense? If we're adding an infinite amount of things, we'd only usually write this when we get a proper number out. So something that's finite. So when can we add up a load of things and still get an infinite amount of things and still get a finite number out? That's when we're adding things that become smaller and smaller and smaller. Imagine, for example, you're taking a half plus a quarter plus an eighth plus a 16th and so on. Try it with a piece of paper. You're going to take half the piece of paper plus a quarter of the piece of paper plus a 16th plus an eighth. You're eventually going to get to 1 if you add up an infinite amount of them, because you're adding up smaller and smaller and smaller things. You can't get any bigger than 1. Sometimes you will see this sign without limits. Now this isn't strict mathematical notation, this is like wrong mathematically, but it is something you see very commonly written down, especially in handwritten notes. When you see this, it's because the limits are implied, because you know the xi's come from a certain set. Usually in statistics, if the xi's are the points of a data series, so the xi's could be the heights of everyone in a certain population, and we sum them across all the heights. We usually don't, if we're just doing this shorthand quickly on paper, we don't usually write the limits if the set is implied. But that is mathematically wrong, but it's good for you to recognise it and still being able to understand it. Okay, thank you. I think that's it for the recap. You will be seeing these sort of things throughout this module.